Good evening. Welcome, everyone. Good evening and welcome back for another virtual science camp. I'm really excited tonight to welcome another great speaker from the Joint Institute of Nuclear Research, Mark Shirchenko, who's going to be talking about neutrino mysteries. So you guys may know neutrinos are one of the least well understood particles, one of the most elusive ones. And at the Joint Institute for Nuclear Research, they've got the most advanced facilities in the world for looking at this particle. So when they offered to do a couple of guest lectures for these camps, one of my first requests was to do something on neutrinos, because really they're the best people in the world to be able to learn about this. And I'm really pleased to be able to have Mark talk to us about them. Just a couple of things before I turn things over to him. For most of the talk, we'll want to focus on what he's showing and what he's doing. So I'll ask you guys to keep your microphones and your webcams off until the question and answer period. If you guys end up having questions that come up with what he's saying, feel free to write them in the chat. Most of the questions will wait till the end to not interrupt the flow of things. If there's anything that I think seems really urgent, or if there's a good time to try and interrupt, I might interrupt Mark, but let me decide on that. So I'll be keeping an eye on the chat and kind of curate what you might want to ask him. Then at the end, we'll have a question and answer period where I'll try and group your questions together. If you want to get on your microphone and ask the questions, you'll write that in the chat and we'll call through an order like we've done in previous sessions. With that being said, I almost forgot to mention, and I'll mention at the end as well, there's a drawing competition that I've just been told about that they're organizing at the Joint Institute for Nuclear Research. So I'll be sharing a link in the chat at the end of the session for anyone interested in doing that. It sounds like a really good competition. I'm disappointed. I just narrowly missed their maximum age. It's from 7 to 35 years old. Some of you who know me well might know I'm 37. So if I had a time machine, I'd go back and compete in this one. But you'll get details on that at the end of the talk. So Mark, thank you again for joining me. I'm really pleased to have you on here, and I'll turn things over to you now. Thanks again.
Okay, thank you, Michael, for having me. And okay, I'll try to start the demonstration. Actually, I changed a little bit the name of my talk. It's of course about neutrino, but it's not like the mysteries of neutrino right now. It's like chasing the ghost. And in the next 40 minutes, I will try to explain you why we call this particle the ghost and why we're chasing it. And because when you talk about the mysteries, looks like they are still unsolved, but we are trying really on chasing it and really trying to discover and understand those mysteries. So that's the idea. And also, here you see some nice pictures, and that's the real experiments. And maybe about at least one of them I will mention in my talk, because I do not have so many time to talk about everything in neutrino physics, because it's a really huge thing, and I will show you it also later. So all it starts actually, and when I start to prepare the lecture, it makes me think of what is similar between scientists, for example, and children or students or school students with what I'm supposed to talk about. And actually, I understand that that's the question about the question that keeps bothering your mind, the question that always makes you anxious and thinking about it just up to the end before you finally discover or just asked, if you're a child, the answer. And as an example of this childish question is the question like why the sky is blue, why the wind blows, and so on. But if you look thoroughly at the question the scientists ask, they're pretty much the same. For example, one of this question is what was before the very beginning? It maybe looks a funny question because, okay, that's the very beginning and what should be before it. But actually, it's one of the central question in modern physics, because all of you maybe know that our universe started with a Big Bang, but then the question arises, what was before the Big Bang? And there are plenty of efforts, plenty of attempts to to answer this question, but still it is on the table. And one of the funniest answer I heard is like this: you know that Big Bang was the start of everything. Everything means the time also. So it's the question what was before actually the time question. That just doesn't make sense. So maybe that's the answer, but we keep looking for another one, because as for me, I personally do not like it. Seems to me some kind of tricky answer. And also there are plenty of questions we try to answer. For example, how the Big Bang happened, and what was the universe like when it was so small and so young that we do not know how even this dense matter could survive, could be alive. Then another question, and why we are made of matter but not antimatter? Why the me and you and even laptop or earrings with the help of what I'm talking right now with you, why it's all made of matter? Why there's no symmetry between matter and antimatter? Why there are us, but there are no anti-us somewhere? And that's all the question of for the modern physics. Also, there's funny thing, because we have huge machines that are looking up to the outer space, and they find out that there are some particles so energetic that so you can compare them with a ball, with a tennis ball at the serve. So they have macro energy. You could feel it, but it's all this energy actually in one tiny particle. And how these particles could what the origin? How can they? What could gave birth to these particles? Is also the question. What happens inside sun? It's also and supernova stars, for example, because all we can see with our eye or with our telescope is just a surface of the sun. And if you look a little bit closer and a little bit deeper in the sun, there's just a hot, dense matter, and through it you just cannot see. And is there any tool or anything that could help us or to answer this question? And the possible answer that there is such a particle, and that's neutrino. And neutrino, it's not only most distributed particle in the universe, but also the most mysterious. Because if we look for this standard model of elementary particles, which is basically like a periodic table for the elementary particles, you can see that neutrino of different kind plays here a certain role, and even you can say that they almost 1/4 of all the particles. But still, if we ask ourselves what we do know about this particle, it was invented 100 years ago. It was experimentally discovered 70 years ago. But still, if we ask ourselves, what is the neutrino mass? We don't know. We just know that there is mass. We are positive about this. We know that the mass, there is a mass. But what kind of mass it is, we don't know. The next thing is how many of them. I just showed you three neutrinos, but maybe there are some ideas that could be 4 or even 6 neutrinos, and only 3 of them are interacting somehow with our universe, and 3 of them are just sterile and do not interact at all. And concerning these 3 types of neutrino, what the hierarchy between them? Which one is lighter? Which one is heavier? What are their look-likes comparing their masses? It's also the question we also do not know. And even the type that in this sector, there are particles of 2 different types, namely Majorana and Dirac neutrinos. And we also do not know which type of this. And the answer for any of this question will immediately, okay, but maybe not immediately, but in the horizon of like 10 years, would win you a Nobel Prize, definitely, because it's the questions that science really is thinking about. And the problem is actually that there is a mnemonic rule that the smaller the particle, the bigger microscope you need to discover it or to understand its properties. And if you look at the very start of the modern physics, like observation of the X-rays. You just need a cathode tube at the table experiment. Then for discover the origin of nucleus, or the nuclear structure of the atom, you actually Rutherford needs a lab. Works with radioactivity. For this works, there was a need to make an institution, and discover the lightest quark requires accelerator. And I do not speak about the heaviest quark or even Higgs boson. You know, that's the huge machines. And what about speaking of neutrino? Why it's ghost, and what machines do we really need to understand it and to discover it? So first, let me put some numbers. Per one atom in universe, there is 1 million of neutrino. 1 billion, I'm sorry, 1 billion of neutrino. 100 trillions of neutrino penetrates through your body per day. But through the whole your life, only one of these neutrino actually interacts with you, or will interact with you, interacted with you. But still, it's just actually, when I make this calculation, I assume a huge lifetime over human. Maybe, of course, there's scientists like me who do the neutrino physics, who are more close to the neutrino sources, and maybe I think at least 10 or 15 neutrino already interacts with me, but I still didn't feel it. Of course, for building such a huge machine, you also need a huge facilities. And here I'll show you just a control room for European Organization for Nuclear Physics. I showed you on the right side, there's a Tevatron and Fermi National Lab in US. And in the middle, there's a NICA facility that is in our institution. And our institution is also quite big. And that make us possible to make such huge physics. Sorry for this slide in Russian, but actually I think you will clearly see that we have 7 labs, 4 of them which is devoted really for nuclear and particle physics. One quite new, comparatively new, is radiation biology lab. And we also have a laboratory for information technologies, because all of these experiments asks the supercomputers, and it really give a lot of data and so on. And also we have theoretical lab, which really helps us to understand to make some calculations and so on. And in our institute, you also can see here, we have 18 member states. So we have 18 states, 18 countries which are members of our institute, and almost 5,000 of employees. Among them, it's 1,200 is actually the scientific personnel, and almost 1,000 is also the engineer and technical personnel. And I really hope that, I just heard about it today, that within like 5 or something years, also France and Germany and Italy will also supposed to join the institute. And we are actually, one thing that we are really popular and well known between the people who are not even connected with physics, and that our institute is connected with periodic table, and we actually, many of elements were not discovered but synthesized in our institution. And there's even a joke, and everyone guide for the tourists in our town keep saying this joke, that there's unique man, he's the only one on the earth who could write his usual mail address using only the symbols of periodic table. So it's it looks like this. So you have ruthenium, which is basically Russia. You have Moscovium, which is Moscow region where we're located. That's Dubna, our town. That's Florov Street, and that's man that is in charge of doing this business is Yuri Salakovich Oganisyan. So that's the quite unique man. But going back to neutrino, you can see here the Congress at Solvay in 1927, and you see here it's almost the whole of the elite of the physics of those days. But if you look for the conferences right now, that's the main conference in our field, neutrino, you can see that there are lots of people doing just one not that big part of the science. And you should also keep in mind that each of this person is actually represents a group or even the lab. So you see that there are many people in the world that are doing neutrino physics and interested in it. And also, I just made there's kind of a plot. On x-axis there's a time. On y-axis there is number of discoveries in our field, in neutrino physics fields, and you can see the fast growing of this field. And also with the black, I marked the Nobel Prizes devoted to the neutrino physics. And even a couple of years ago, there was another one. There was fourth Nobel Prize also connected with neutrino physics. That's why we sometimes call neutrino Nobel Prize generator. And what kind of neutrino could be? Let's do finally for the topic. What kind of neutrino they could be? So the very first neutrino is the relic one. That's basically the remnants of the Big Bang. So they're from the early universe. They are very, very cold, as we say. They have very, very low energy, and they're making some kind of this neutrino gas, which is all around us. And because of this gas is cold, because it's very low energy, we still do not know, and we still do not have any ideas on how to discover these particles. But we know they are, but we cannot still detect them. So maybe it's a question for you if you're going to connect your career with the neutrino physics. The next thing is the next most distributed, the biggest flux right around us is the sun, and then that's a quite big energy. We can already detect it, and there are some Nobel Prize. For example, here it's Super Kamiokande detector, which was devoted to the sun neutrino problem, and this one thing actually sees the inner core of the sun, because you could imagine that even light or even some particles that are just were born in the core of the sun needs hundreds of thousand years just to break off this gravitational trap and break off this hot dense matter to finally reach us. But for neutrino, it's only 8 minutes to go from the core of the sun right to us. So that's the next, the second type of neutrino. The third type is the atmospheric neutrino. Remember I told you about these cosmic rays that are very, very energetic. Just imagine that they're going to our atmosphere. Then they collide with the atoms or molecules in atmosphere. And because of they are very energetic, they give you a multiverse of many particles. Among them, there are also plenty of neutrinos. We call it the air shower. And these neutrinos are also well detected and well known. Then we go to some artificial sources with what it's much easier to work, of course, because you somehow can control this source. The very first one is the reactor anti-neutrino source. And that's the just usual power reactor, or maybe scientific reactor, but still it's the huge source of neutrino. The very last one is accelerator neutrino. That gives you some beams, and this also nice because you know at the exact time of neutrino burst, and you could this neutrino goes along very long direction, then you can make on their way some detectors and see what happens with neutrino from 100 kilometers. And you see here, maybe not all of you know what is the logarithmic scale is, but if you try to put all this neutrino on a plot like energy versus flux, and you really want to make this plot, you just need something like, I don't know, maybe from here to the end of our galaxy. But that's why we physicists use some kind of a trick. We use this logarithmic scale, and here each one division is not like +1, but multiple 10. So you see here, then you have a nice picture, but you see that's the neutrino here have an energy like 1 with 18 zeros, and here you have neutrino like 0.1000001. So that's the huge, really big gap between neutrino with the smallest energy and neutrino with the highest energy possible. So let's finally talk about our, I think, main project of our lab, and it's devoted to the neutrino from the very depths of the universe, for those neutrinos that I told you that we still don't know what was the origin of it with such an energy. Actually, if you consider the processes in the universe, you will see that almost everywhere there's some kind of neutrino. It is emitted. It is maybe in some reactions or so on, but still it's somewhere. So it's even like a common phrase, like if something interesting is happening in the universe, you can be almost sure that there is a neutrino nearby. And right now we know that our knowledge about universe are really incomplete. We just more or less know 5% of the universe, which reflects the normal matter. But we do know that there is 26% of the universe with some dark matter. We still don't know whether it's particles or something else, or I don't know, maybe waves, maybe something. And we also know that there is almost 70% of dark energy in the universe that pushes away our galaxies. And also the origin of this dark energy is not known. So that's why it's really, there is a real need in construction, some kind of a machine, of a tool, of an instrument that look for the particles, especially for neutrino, from these sources. And very first, and one of the very first, and one of the common idea was registration neutrino through the Cherenkov radiation. So here we just you also imagine about the neutrino that penetrates the Earth, and in some medium, maybe it could be Earth, it could be water, it could be ice, it interacts with the matter, and then gave birth to the new particle, which calls muon. And this muon is really energetic. Also, it travels faster than the light in this medium. You should pay attention on this. I'm not talking about violation of Einstein rule that there's nothing that would travel faster than light, but the light in vacuum. But in medium, there is such an effect, and that's actually called the Cherenkov effect. And when this light, when this particle emits, when it travels, when it's transversed through medium, it's really give origin to some kind of radiation, which calls Cherenkov radiation. And it's in mathematically and almost similar to the plane that crosses the supersonic barrier. So when the plane crosses this barrier, you can hear some kind of a bump or whistle. And here it's almost the same, but not like the sound wave, but electromagnetic wave. And you can clearly see this cone, and you can measure this cone, and the angle of this cone is actually is corresponded to the energy of the initial particle. So it's really nice idea how to measure it. And to use this idea, you really need some kind of a clear medium, because you need this light to be not to be trapped, not to be saturated, and not to be somewhere be taken. So in Russia there is a great lake, Baikal, which is very clean, and here we just put our detector made of some strings of the let's say tool. So it's actually the tool that helps you to track the light, and we call it photo multiplier tube. And basically, to understand it's quite a tricky instrument, but you can understand its principle like it inverse electric lamp. Because if you consider electric lamp, it's actually the voltage or the current that is applied to it, and then it gives you some light. Here it's vice versa. You have a high energy photon, which is basically light. Then you have this ionization track, which emits some kind of light also, but low energy. Then you have for the cathode, which transfer the photon into the electron. And then you have this, you see this here, that's some kind of gates that they give birth to additional electrons. And then here you just see a normal current and you can measure it. Because actually what we do in physics and science, which we actually can measure, it's basically the electromagnetic interactions. It's the best interaction we can measure. So we always try to put all the interactions in the world into electromagnetic one to measure and to deal with it. So that's the thing about it. And you see here we are in a great depth, like more than 1 kilometer. Here we put our photomultiplier tubes or PMTs, and then we just taken this current and providing it to this shore station. And just to give you the idea of a scale of this, you see here it's Ostankino Tower, but maybe not all of you been to Moscow. It's like, if I'm not mistaken, it's something like 1.5 of Eiffel Tower. So you can see that our instrument is really huge, and maybe it's one of the reasons we call it not some machine but telescope. And there are this telescope usually as a link you use our it could be said that it uses our Earth as a length. So here these muons are originating, and here we just track them. So the idea is, like, we being on a north hemisphere, we just searching the south hemisphere of the outer space. It's particularly interesting because on the south pole of the hemisphere there is a center of our galaxy with a huge black hole and plenty of other interesting things happening there. And also there's another telescope like this on the south pole, which calls IceCube, and if you combine them, you can easily track the whole universe, the whole 4 pi angle. Here you just see this PMT. You see they're quite big, and that's not also because you need to track the small amount of light, but also you need a big glass, because as I told you, you put them right down 1 kilometer, and there, of course, the pressure is 200 times larger than here we have on the surface. So they should survive it. There should be some kind of a body scuff or submarine, like, but they should survive, and no one drop should be there. It's really a huge problem for us. And that's how they put it during the winter. We're also lucky because during the winter we have an ice on the lake, and then you just make a hole and put it there. And that's the kind of expedition that each of the physicists that involved in this project should make. It's kind of, I would say, some kind of and here's the video. I really hope that it will not be slow, but just to keep it in for you to keep it in mind, let's pretend that there's some process here. It's a emission from the black hole of some energetic rays, and some of these particles reach the Earth, penetrate through it, and in the lake of Baikal, they give you these cones of Cherenkov light. And also on this 1 kilometer depth, you can see the same cone I just showed you, and then you have a signal in some of the PMTs, and then its signal goes to the shore station, and then there is several computers and several operators just sitting there and looking for what cons they were, from what part of the space they were coming, what particles what is initiated, and so on. And here you see this is actually the part of this expedition that now they put the PMT down under the ice, and you even see that they called some aqualungists just to picture this from inside, and you will see here right now that they're when they put it there, that's how it looks like down in the lake of Baikal. So that's actually the one experiment that I have time to talk about, but there are a bunch of them even in our department. So if I just put them on one slide, and you see there are many of them, and some of them are really nice. So there's an experiment dance which I'm participated in, and actually you can see that my name here is dance just because we have some kind of a working conference, and I just forget to change the name. And that's on the the experiment on the power plant, where we're searching for these new types of neutrino, for example. There are also many of them. That's the accelerator experiment. That's some experiment devoted to the rate decay with the neutrino, and so on. And there's also, I always like to talk about this. That's the funny experiment, and I call it second derivative for the experiment, because in some of these experiments that I mentioned before, there is some theoretical uncertainties, and to help these guys in the theoretician lab, for example, to help to calculate better, we do another experiment. So that's the experiment for help theoreticians to calculate the another experiment. So that's why I call it the second derivative. And there are always questions about the practical usage of neutrino, because they say it looks like this. Okay, that's a really funny thing you are talking about. That's mysteries, that's universe, that very start, the Big Bang, and so on. But what the practical usage of the neutrino could be? And to approach the answer for this question, I will just briefly tell you 3 stories. The very first one, if we were in usual auditorium, I would ask you to answer this question, but right now I just put it under these black boxes. I will show you and answer it. So one of the physicists was asked about, what do you think the something you discovered will find the practical application? And he said, just immediately, he said, never. There will be no applicable usage of my discovery. And who is this guy was being, and about what he was talking about? Actually, it was Rutherford talking about the nuclear energy, and he talked about it just 5 years before the launch of the very first nuclear reactor, and 8 years before the explosion of the first atomic bomb. Of course, it's the worst thing that scientists could imagine about the usage of his discovery, but still, that's even the great Rutherford could not look ahead about what could be the practical usage of his discovery. The second one is another approach when the physicists do something for themselves, like the HTTP protocol, which actually helps even us to talk with each other right now. But no one knew this time, back in 1989, that there will be some ideas that this protocol would be so great, so fast, that will make a World Wide Web around it, and that will be the thing without what we cannot even imagine our life. And the third thing is about transistor. It actually was the tool that was thoroughly prepared, and there were put a lot of efforts to make it, but finally just some funny thing was made. The guy in the lab just put the voltage not the right way but inverse way, and then only the transistor worked, and then it makes it a great great thing, and actually all of us have millions of them right now in our pocket, and that's a mobile phone. So the real answer about the practical usage of neutrino, the real honest answer is we do not know. But I just put some ideas. It's almost you can treat it as just my thought, my take on this, and I order them in also on it's my take, in some kind of imaginary line from the most the most normal one, maybe for some kind of imaginable idea. So the very first thing is multi-messenger astronomy. So we want to look into space not only with our telescopes, not only with our radio telescopes, but also with gravitational waves and also with neutrino detectors. So if you combine all of these radiation waves and particles together, you have some holographic picture, I would say, of the event in the universe, and it really helps you a lot to understand what is going on there. The second thing is the research of the main nuclear reactor, which is basically right in our planet. They are so hot in the core that there are some nuclear reactions also are going. So, and there are some not the ideas. There are some detectors that's already checking and monitoring and trying to discover the power of this reactor. Also, that's the thing that we right now are working on. It's non-proliferation of nuclear weapons, because when one of the easiest idea to make a nuclear bomb is just to extract the plutonium from the usual power reactor, which is basically the bomb itself. But with neutrino, you can actually see the difference in spectrum and in flux when you extract this plutonium. And you can easily say that, okay, there are some bad guys that are extracting plutonium and they are preparing to make a bomb. And another thing is that already talk is the matter antimatter thing. And maybe when we just put it in our hands, that makes us to make some kind of an accumulator of energy or something like this. But for know this, we should know the difference between matter and antimatter. Also, the next already some kind of a science fiction thing. It's ultra high speed communications. Right now we have satellites, and if you want to provide the signal from, say, Australia to Canada, you just need all these satellites to go through. So you just they're making their long curve around the Earth for the signal to reach the final destination. But with neutrino, as I already told you, the Earth is quite transparent. So you just need to put the bunch of neutrino just through the Earth, and immediately it will be on the other side of the Earth. Also, there are some ideas about looking for mineral resources deposits in the Earth, but right now there's some working prototypes for the neutron, what they call neutron carotage, but they could also be a neutrino, but for the just deeper things in the Earth. And the very last thing that I think it's just, yeah, that's full science fiction. It's, yeah, we remember that neutrino travels along a lot of distances without any distortion of the signal. So that's maybe the key thing about for negotiations, even with alliance. And okay, right now I'm finishing, and just to finish, I will tell about the great book. I don't know whether there are many translations. I know there's a translation on Russian. I don't know whether the translation in French or some other languages, but you definitely could easily buy it from Amazon. It's really great book about the neutrino history and the mysteries and so on. And it's not like 40 minutes lecture. And there's also very, very nice phrases for that also stays in your mind, and you're really, it always really pleasant to tell something like this. And I personally really like the phrase, in science, the most common phrase that precedes the new discoveries, it's not eureka, but this is strange. And just because of our host is in Paris, I already made a mistake and put some slide on Russian. I want to finish with a French phrase, but excuse me if my pronunciation is quite wrong. Personally, I learned French just a long time ago, and this is the phrase from one of the greatest writers of France and one of the greatest writers in science fiction field. And the phrase is "Le temps viendra où la science dépassera les fantasies." That's a Jules Verne. And for those who, as me, do not know French well, the phrase means like there will be times when science surpass the fantasy. And I think we're lucky enough to live in such times. Thank you very much. So that's the end of the talk.
Excellent. Thank you. That's been really enlightening. Thank you so much for taking the time and sharing this with us.
Thank you very much.
And so now we'll have a little bit of time for questions and answers. So if anyone has any questions that came up over the course of the talk, please add those into the chat now. There were a couple that came in by direct comment through the chat. So maybe I'll start off with those while giving a minute for anyone else who wants to ask something. So there's a question that came up about neutrino flavors. And it was, if I can ask you about the change of neutrino flavor while in flight. Is that something that is possible to try and explain in simple terms?
That actually was a task, and I don't know that without any pictures I could explain it. But the idea that could track it, like you know, that different flavors consists of different masses. So there are 3 masses and 3 flavors, and each of the flavor is not like corresponding to one masses, but some kind of mixture of each masses. Is it clear? So
like a range of masses, right?
Yep, yep. So then when neutrino flies, it flies not with the speed of light, and the huge masses travels slower, and light masses travels faster. And then in some way, in some distance, you can discover that this mixture is not corresponds to the this electron, for example, flavor, but corresponds to muon flavor, and that makes really makes the neutrino oscillates. So that's different in the masses. So maybe it's not the really right explanation, but just to give you an idea how it has happened, I think it works.
Okay, that sounds great. And the person who asked that in the direct chat, if that wasn't clear, you have any follow-up, let me know if you want any more detail on that. There've been a couple more questions that have come through. I'll group them together if there's any similar ones. The next one, I think, is asking how can neutrinos code information? And I think that was probably when you were mentioning one of the applications, like for high-speed telecommunications.
Then the idea is quite simple. There are plenty of properties in neutrino. One of them could be, I just imagine on the way. It's not like the ideas of some scientists, but you can put this. For example, neutrino has helicity, which means actually what is when it travels, it also rotates, I would say, and it could rotate on this direction, on this direction, and you can just use it as 1 or 0. So this rotation could you could code as 1, and the vice versa rotation you could code as 0, and then each of the neutrino could bring this information. But of course, it's just an idea. No one still right now could make or prepare the neutrino with a specific helicity, unfortunately.
And one thing I'm wondering, and this isn't one of the questions, but it, like me thinking about the response, and hopefully some people are interested in hearing this question as well. If you want to detect the helicity of neutrinos and code a potentially large quantity of information, then wouldn't we need to be able to detect neutrinos significantly more sensitively than we are? Like most neutrinos pass through everything.
Definitely, I think it maybe it even works like this. We're not put this information in just one neutrino, but we put in this information in, say, millions of neutrino. So we have first slide or first bunch of neutrino with one helicity, the next bunch with another helicity, and so on and so forth. And from this, you can then collect at least 1 or 10 neutrinos, and you can then recover the information that was brought from this atom, or what do they call this guy in this information theory.
So it would probably need to be built on a probabilistic model if we're expecting to miss most of the.
Yes.
Okay. Oh, that sounds like a really interesting thing. I want to ask more questions, but I'm going to get to some of the participant questions.
Okay, fine.
There's one asking about your experiment, DNSS, and you mentioned it, but I think this person is asking for more details. Can you briefly add more about that?
Yes, I will try to open this presentation again.
So it sounds like it might be a question that could lead to like another long lecture.
It is actually, it was in my lecture, and finally, when I just tried this morning to go through, I understand that it's even more than an hour. That's why I just removed from the lecture. But okay, just let me have some couple of slides on this. Okay. So if I could bring it. Okay, so this is the slides for these experiments. I will briefly will go through it. Oh my God. So idea here that we use a usual power reactor. And what is power reactor? Power reactor, it's like 3 gigawatts of thermal power. I talk about this, the Russian detectors VVR100. And the core is like they're like a cylinder with a diameter of 3 meters and a height of almost 4 meters. And there is 70 tons of uranium. And then this uranium is burning during the campaign and giving the electricity. But the anti-neutrino flux is really enormous there. It's like 10 to 20. So 10 with it to 20 zeros per second. So that's why make these reactors interesting. And actually, if we look on this, that's a how to say this layout, not layout, but okay. This is the reactor, and here you see the core, and we just put our instrument right here, our detector right here. So we're really close to the reactor core, and that's how our detector looks like. I wouldn't say about the principles. Maybe if somebody wants, I will explain. So there are plenty of these little long detectors combined together, and then we also collect lights here, but that's the lights from some other reaction, not Cherenkov light, but inverse beta decay light. But nevertheless, we collect, and we also can say about that's the thing. In the shielding, and there's 1 cubic meter of our detector, and actually this flux makes us speaking about the fluxes and information. When Pauli introduces neutrino, he said that I do the worst thing for a theoretician. I invented the particle that no one can discover, And it was discovered in 20 years. And right now on this power plant, we have like 6,000 of neutrino per day. So that's the world record. And we actually see that's a multi-purpose detector. It's also devoted to non-proliferation of nuclear weapon, but it also just monitoring the power reactor. We can say what is the immediate power of this reactor and so on. And we also want to see this in other types of neutrino, this sterile neutrino, because you see here it's on some lifting gear. And of course, if you put it closer to a reactor, you see more of them. And if you put it far from a reactor, you see less of them. But there should be as 1 per distance square law. And if you see some distortions of this law, then it means that you have some losing of active neutrino somewhere in between, which basically will tell you that there is a sterile neutrino. That's okay. That's our detector in brief.
Excellent. Thank you. Just to make sure I understood, because also if I'm making sure I understood, hopefully that helps make sure participants have understood. When you're talking about it not violating the inverse square law, it's assumed that it would follow that if the neutrinos aren't interacting with anything, right? And so if it doesn't follow that, the only other the possibility is that it would be less or it would be more. If it would be less, the neutrinos are interacting with something we wouldn't think they're interacting with. And if it's more, there's some unknown source of neutrinos coming in, right?
And you can say about the source of neutrino if on the distance you see more neutrinos than square law predicts. But we're looking about not excess, but some lack of the neutrinos. So the idea actually it was the idea of some guys from France when they just thoroughly calculated the flux of the neutrino from the reactor, and they say actually we see the miss of 10% of them, and that's what makes even us and plenty of people around the world doing this business and making these detectors. And the basic idea was, okay, we measure, for example, on some distance, and then we double the distance, and we should see 4 times less neutrino if everything is right. If neutrino just goes like this and spread out from the reactor. But if you see like not 1/8, but 1/4, but 1/4 minus 10%, then it's hard to explain there's something else but the sterile neutrinos.
And do they have any idea where the missing neutrinos, like what happened to them, where they got absorbed, where?
Maybe let's put it like this. Maybe I'll pretend that I'm a busy guy, but actually I'm too lazy. But I right now, from the first time, I just look into the archive, and everyone, I think we with Michael definitely know. But if you don't know, there's a huge archive of scientific papers that is free, and you can put there your ideas and so on. And there are a bunch of these papers that really trying to explain the deficit of this neutrino. And from the on the very start, I'm trying to look for them, and there are plenty of ideas. And finally, I just stuck out and give up with reading all this, because personally, I do not believe on the sterile neutrino like this.
So there's still a lot to find out.
Yes, it is. But actually, we almost closed these neutrinos that were invented by these guys. We think right now we're just almost close the question.
Okay, that's excellent. And just looking at the time, are you okay to answer a couple of more questions before I cut things off?
I'm here for you.
Okay, perfect. There was one that came in from a direct message asking about, why do neutrinos only come from black holes? And I'm not sure if that is the case, but do you have an answer for that?
No, definitely not. I'll show these sources of the neutrino. It's not like only the black holes. black holes makes the neutrino or any other particles energetic. That's one of the most energetic source of the particles we could imagine right now. But it's not the only source. The most part of the neutrinos in our universe are from the Big Bang.
And that's kind of related to another question, which is about the energy versus flux graph for the neutrinos. And this question from Xavier is asking why each type of neutrino has a similar shaped curve, saying like an upside down hill, or hill upside, or an upside down Nike swoosh.
It's always, I think it's always the thing about the nuclear physics. You have always some resonance. So in each of the source, you have some kind of, if we do not go into the details, you always have some kind of reaction. And this reaction is actually the specific energy. Of course, you have some of this reaction with less energy, some with more, but there's always some kind of a peak on the spectrum.
Okay, excellent. Thank you. Then there's a question about something about magnetic moments. Sorry, just looking back up through that.
It's great. They just maybe it's for third or second question about my PhD. I really like it. The one was devoted to the helicity, and now it's about the magnetic moment that's also in my PhD.
Oh, excellent. That's great to hear that we're right on topic for your favorite topics. So this one is wondering if neutrinos have a small magnetic moment that's just so small we can't detect it yet, and how we might be able to how would this affect detection?
So right now the answer, we do not know. We have some limits on this magnetic moment. And right now, I just showed 3 experiments on our nuclear power station, and one of them, new GEN, is devoted to the neutrino magnetic moment. And we were trying to push the limits to another order. And the idea there is when neutrino interacts with the matter of your detector, we use the germanium detector as a medium. There are several possible cross-section, several possible processes which can lead to distortion of the atoms in your detector. So the one is weak interaction, the one is electromagnetic interactions, and there could also be coherent scattering with the whole of this. But right now, if we're interested in this electromagnetic interaction, so you can calculate the impact of the weak part. You can calculate or measure the impact of coherent part, and also you see that all the other part is just electromagnetic interaction, which basically means that your neutrino has a magnetic moment or some kind of a milli charge. That's the idea somewhere. There are some papers on whether neutrino could have some milli charge.
Fascinating. We have 3 questions that seem to be left. If we don't take any new ones after that, are you okay to take the time to that, or do you want me to pick one of them?
It's okay. Let's. If people are still there, then let's ask the questions. Let's answer the questions.
Okay, perfect. So there's one about the Baikal telescope, how it focuses the neutrinos from the Earth, or I think because you'd said the Earth is the lens, so like they're wondering how.
Yeah, that's always the question when you just maybe do the bit wrong analogy. It's not actually a length; it's actually a moderator. So it's a medium in where the neutrino interacts with matter. It's not like the length like it's focusing. It's just a moderator where this interaction of big numbers of neutrino could happen.
Okay, thank you. And there's one about if JINR, and this one's a bit more general. It was asked in the direct chat. Does JINR have any experiments or research to support current controlled fusion power station research programs? Like, so I guess like cold fusion, is there anything going on with cold fusion there?
I think that JINR somehow involved in the ITER project, and I don't actually know the guys who are involved in this. And there were also, unfortunately, this work I think is over, and it didn't. Somehow it happened. Sometimes it happened. It didn't lead to any success, but there was idea that cold fusion could be made with help of the muon. I told about the muon. Muon is actually the heavy electrons. So the idea was like you have some kind of a proton, then you put muons on this orbit, which is actually quite close to, because of this mass, it's quite close to the proton. Then you have some kind of something like neutron, because the overall atom is actually neutral. It's muonic atom. And when you put close to another proton, that could lead to this cold fusion. But actually, muons are quite expensive, and that's why this idea didn't work. And I don't know actually whether JINR is involved in some other kind of cold fusion business.
Okay, thank you. And the last question is one on antimatter versus regular matter. You'd asked the question, and I think this is right at the beginning of your presentation, why we're made of matter, not antimatter. But did you answer that question?
No, and nobody does. You know, there is some kind of a process in neutrino physics that looks like there are prefer matter final stage over the antimatter final stage. And that makes the idea is like during this what they call leptogenesis, during this whole years of the universe expansion and evolution, this small, just very small difference between matter effect and antimatter effect finally leads to our universe where we have only matter.
Okay, excellent. And that is the final question. That actually leads to a good transition to me reminding the participants about upcoming camps. So I'm just going to spotlight myself for a minute to mention upcoming camps. So those of you who participate in a lot of them probably know that there's going to be a 2-week break from the camps. Then we'll start back up in March. The second one in March, on March 9th, that's actually going to be Jeff Wiener from CERN back to talk about antimatter. So if you have more questions on antimatter, then save them up for...
I have.
So it'd be wonderful if you come to Jeff's talk to ask him.
Okay,
although from one physicist to another, like I can give him you his email, or like, you know, you could ask that way. But if you want to attend, that'd be amazing if you come to Jeff's talk.
Okay, fine, I'll try to.
And there's a couple more exciting ones from JINR coming up. The 16th of March, one on the brain in space, 30th of March, one on the Monte Carlo method. All of these are going to be in the schedule, which I'll send out to everyone who signed up for any of these camps once I finalize a couple more details. So it'll be coming out later this week. Also, exciting thing coming up during the last half of February. So we won't have any of these regular Tuesday evening or Saturday evening camps. I had been planning on going to Ghana, West Africa, where I do volunteer work training science teachers. With the pandemic getting a bit worse, that's been canceled. So the replacement is going to be a couple of virtual science camps that are a virtual museum pass, checking out some museums around Paris, inviting you along to check them out. And with these, there'll be some virtual tours of CERN, including the antimatter factory. So we'll get to see more about antimatter. This is brand new. I just canceled my flights a couple days ago, so all of it's being thrown together last minute. You'll get a schedule for them by the end of the week or so once I get things together. But there's exciting things coming up for those of you interested in joining more virtual science camps. I almost forgot to give everyone the link to the drawing contest that JINR is running. So it's in the chat now. It sounds great, although I can't honestly say I know that much about it, but I am disappointed I'm too old to participate. So on that note, I want to thank Mark again. It's been amazing having along for this. I know I've learned some stuff. I'm sure the participants have. So thank you again.
Thank you for having me. Thank you. Thank you very much.
And have a great evening, everyone. Goodbye and stay curious.